Think SUVAT is the answer to every kinematics question? Think again. If you try to use one formula for a journey where the acceleration is changing, you're walking into a trap. I've analyzed the kinematics questions from all 4 2025 summer variants, and the examiners are getting sneaky. Today, I'm giving you the Kinematics Toolbox you need to decode any graph and crush any calculation in under 60 seconds. First, we have the SUVAT equations. These are powerful, but they have a strict limit. They only work when acceleration is constant. If you see a curved line on a velocity-time graph, or if the slope changes abruptly, like we saw in MCQ 5, you cannot use one single SUVAT formula for the whole journey. Second, master your gradients. On a displacement-time graph, the gradient is your velocity. On a velocity-time graph, the gradient is your acceleration. Third, and most importantly for paper 1, is the area under the curve. The area under a velocity-time graph gives you the displacement. If the area is above the x-axis, it's positive displacement. If it's below, it's negative. Toolbox packed. Now, let's see how the 2025 examiners tried to trip you up. Starting with a pure calculation from paper 14. Here's the first question. We have a ball released from rest at 12 meters. Air resistance is negligible. They want the time to reach the ground. Check the toolbox. Is acceleration constant? Yes. It's free fall under gravity, and air resistance is gone. This is a green light for SUVAT equations. Now we write down all the variables clearly. We need the equation that links U, S, A, and T. This is the one that we need. By substituting the variables and solving the equation, we got T equals 1.56. Look at the options. C is 1.6. That is a clean 30-second mark if you don't overthink it. But watch what happens when the journey gets more complex in our next question. Let's look at this question from paper 12, where the units are the real enemy. We have an aircraft starting from rest that needs to hit 85 kilometers per hour within a 1.2 kilometers runway. We need the minimum constant acceleration. Our acceleration options are in meter per second squared, but our data is in km an hour. Now, before we touch our 3 main tools, we have to bypass the examiner's favorite trap, units. Think of this as the secret tool 0 of your toolbox, as it must be applied in all topics. Let's fix that first. So we have U equals to 0, as the aircraft is initially stationary, V equals 23.61 and S equals 1200. Check out Kinematics Toolbox. The SUVAT's equations could be applied as the acceleration is constant. We choose the equations that consists of U, V, S, and A. Therefore, this is the equation that we should use. Substitute all the corresponding values and solve the equation. Finally, we got acceleration equals 0.232. So the answer is option A. If you didn't convert those units, you'd be nowhere near the right answer. Unit traps are one thing, but graph traps are where most students lose their A-star. Let's tackle the boss level of velocity-time graphs. This question is a classic. Many students see a straight line and try to use one SUVAT formula for the whole 10 seconds. Please don't. Look at the slopes. The acceleration changes at t equals 2 and t equals 6. Remember our Kinematics Toolbox 2 and 3. The gradient of the velocity-time graph represent acceleration, while the area under the graph represent distance. Let's look at the options, one by one. Statement A says, the car stops for 4 seconds. Look at the graph between 2 and 6 seconds. The line is flat, but it's flat at 12 meters per second. That means its velocity is 12 meters per second. In a velocity-time graph, a flat line means constant velocity, not zero velocity. The car is still moving fast. Option A is out. Statement B claims the acceleration is 12. Let's check tool number 2. Graph gradient. Gradient of velocity-time graph represents acceleration. So calculate the gradient from t equals 0 to t equals 2. The acceleration is actually 6 meters per second squared, not 12. They're hoping you just look at the y-axis and ignore the time. Option B is out. Now for statement C. The car travels 36 meters in the first 4 seconds. For distance, we use tool number 3, the area rule. The area under velocity time graph is distance. We calculate the area under the graph from t equals 0 to t equals 4. The area of the trapezium is 36. So it is true that the car travels 36 meters in the first 4 seconds. Option C is correct. Just to be safe, why is D wrong? It says 48 meters in the last 4 seconds. So again, we calculate the area under the graph from t equals 6 to t equals 10. The area is 24, but not 48. Option D is definitely wrong. So the correct answer is C. We've mastered velocity time graphs, but what happens when the axes flip to displacement and time? Let's check with this question. We have 4 distance time graph. In our toolbox, tool number 2 says the gradient of this graph is the velocity. Since we have distance instead of displacement, the gradient represents speed in this case. First, the student cycles for 10 minutes to the shop. On a distance time graph, that's a straight line going up. Then, they spend 5 minutes in the shop. Since they are not moving, the distance doesn't change, so we need a flat horizontal line from 10 to 15 minutes. Now, here's the kicker. They cycle home at twice the initial speed. Since it's a distance graph, the line must keep going up, not down. Distance never decreases. That immediately eliminates A and B. Because the speed is doubled, the gradient of the final section must be twice as steep as the first section. If you look at graph D, the final slope is much steeper than the first, and the total distance reaches 2 kilometers. Let's do some calculation to confirm if D is the answer. From t equals 0 to t equals 10, the gradient equals to 1 over 10, which is 0.1. From t equals 15 to t equals 20, the gradient equals 2 to over 10, which is 0.2, which is exactly twice the gradient of the first section. Therefore, D is our correct answer. Always check your axis, whether it is a displacement graph or a velocity time graph. The answer would have looked very different. You've made it to the final boss. This velocity time graph from paper 13 is the ultimate test of your kinematics toolbox. In this question, we need the displacement at t equals 20. Remember tool number 3. Displacement is the area under the velocity time graph. But there's a catch. Part of this area is below the axis. From t equals 0 to t equals 16 seconds, the object is moving in the positive direction. This is one large triangle. Area of this large triangle is 1 over 2 times the base, 16 times the height 3, which is 24. At 16 seconds, the velocity becomes negative. The object has turned around. We need the area from 16 to 20 seconds. Area for the negative journey is 1 over 2 times, 4 times negative 1.5, which is negative 3. Total displacement is therefore 24 minus 3 equals 21. The answer is option B. And that is how you dismantle the 2025 kinematics papers. You ignored the SUVAT traps, mastered the gradients, and let the areas guide you to the right answer. If this toolbox helped you see the patterns in these graphs, hit that like button. I'm dropping the full walkthrough for dynamics and forces next, where we take these same tools and add Newton's laws into the mix. You don't want to miss it. Subscribe, and I'll see you in the next one.